All right, good afternoon, everyone. Welcome back from the lab and from lunch. Hello, everyone on Twitch. My name, again, is Ben Willett. I'm a solutions architect here with AWS. And with me today is Sudhir Gupta, a partner solutions architect. Tell you a little bit about his background.
Hi, all. I am the Sudhir Gupta, and I'm the partner solutions architect in AWS, specialized in Amazon Redshift. So normally, I am responsible for working with ISV and SI partners. Any opportunity related to the Amazon Redshift, like building technical competencies with respect to the Amazon Redshift or data lake, and like validating, certifying the ISV product which integrates with Redshift, and so on. And overall, I have more than 13 years of experience in database and analytics domain. Even I worked as a senior database engineer for Amazon.com, and I lifted, giant migrations, 50 petabytes from Oracle to the Redshift and data lake. So yeah, that's all.
Awesome. Thanks, Sudhir. So I'm going to kick off the presentation. Sudhir is going to come up and deliver the middle, and then I'll come back at the end and wrap things up. Thanks, Sudhir. All right, terrific. So we're going to dive into a little bit of Redshift. We've covered some of this, so I'm going to go fairly quickly. But for the Twitch folks, I want to make sure that we have a good understanding of what Redshift is and a little bit on the Redshift internal side of things. So again, Redshift is a ANSI SQL compliant database with full ACID properties support. So all those good OLTP and all those good transaction processing skills you learned in school are all implemented here. This is a fully managed data warehouse provided by AWS. So for example, you will spin up a Redshift cluster. We will take care of the patching and the maintenance of that cluster. We'll do automatic backups for you. We'll monitor the nodes for health. And we do something pretty slick where behind the scenes, we'll actually have separate copies of your Redshift database spread on different nodes to become more fault tolerant. If a node becomes unavailable, we're able to rehydrate a new node based on extra data stored around the cluster. So good fault tolerance there. As you'll see, the back end is massively parallel, shared nothing, OLAP architecture. And we talked a lot this morning about columnar data store. Redshift really shines in large-scale aggregate reads. So if you're doing things like select average sale price, select maximum sales price, or show me the thing that sold the most on Christmas Day. What was the #1 toy on Christmas Day? Redshift is going to handle those large-scale aggregate reads extremely well. Again, engineered for performance. Sudhir will talk about some real-world scenarios as well as his experience working on Amazon.com. But it's designed to scale, but for 1/10 of the cost of traditional data warehouse solutions. And again, security is absolutely priority #1 at AWS. And we've got end-to-end encryption on your Redshift communication between the client, the server and back, and then we've got encryption at rest in the database engine, and then a number of certifications, including SOC 1, 2, and 3, HIPAA for healthcare applications, FedRAMP for government applications, and many, many more. All these certifications are available on our website, and I encourage you to take a look at them. And then both Forrester and Gartner have positioned us as leaders in their quadrants. So more customers use Amazon Redshift for their data warehouse workloads than anyone else. We've got a bunch of logos up here on the screen, everybody from Johnson & Johnson in healthcare, Liberty Mutual for insurance. We've got Philips, we've got Amgen in the healthcare life sciences division. If you don't see your vertical up here, definitely go to the Redshift page, search for Redshift case studies or customer success stories, and I'm sure you'll find a use case up there that matches your environment that you can learn from. So what does Redshift look like under the hood? So far we've been talking about Redshift as a SQL data warehouse where you've got a JDBC connection coming in or an ODBC connection coming in either from a BI tool like QuickSight, BI tool like Tableau, or maybe it's a custom application that you've written to use JDBC or ODBC as the interface. That's going to hit a Postgres compatible engine in Redshift. And so anything that you can do up against a Postgres database will work here. But behind the scenes, behind that Postgres compatible interface, we've done some pretty amazing engineering in terms of combining a massively parallel processing backend. And you'll see how the Redshift cluster can be spread out across up to 128 nodes. We've got an OLAP engine in there for, again, doing these large-scale aggregate queries. And then it's a columnar data store. And again, instead of doing row-wise operations, when you're doing large-scale aggregate reads, columnar is really the way to scale for maximum performance. So if you put that Postgres-compatible SQL engine in front, and then you've got a massively parallel engine behind it with an OLAP server and a columnar data store, that is what we built with Amazon Redshift. And we've integrated that with all of the AWS goodness that you know and love. So runs in a VPC, uses IAM for identity and access management, who can control the cluster, who can start, who can stop, who can expand the cluster. We'll talk about S3 storage using Redshift Spectrum. And then key management system, again, if you want to have more control over the encryption, you can let Redshift worry about it, or you can manage keys yourself with KMS. And then CloudWatch, right? Very important. Redshift is a massively powerful data warehouse, but you still want to keep an eye on it. You want to understand what your traffic patterns look like. You want to monitor your CPU. You want to monitor your disk. And CloudWatch is going to give you all of that information. And then you can use things like CloudWatch alerts and events to send notifications to make sure that the cluster is performing as you'd expect. So the architecture, we talked a little bit about this, but again, shared nothing architecture. So you've got this thing called a leader node. This is sort of the brains of the cluster. This is going to be your JDBC endpoint. You'll get a DNS name for this leader node. That's where your queries land. The query processor on the leader node will actually look at its metadata. It'll understand how the data is spread out across the cluster. It'll formulate a query execution plan, and then it'll actually break that query execution plan up to into C++ executables that will be deployed on each compute node in the cluster to process the data locally. So the leader node has got the metadata catalog. It's got your SQL query. It understands how to generate a query execution plan appropriate for each node in the cluster. It generates that executable, pushes it down to the compute nodes, and that code runs locally on the compute nodes. So let's take an example. We've got a 26-node cluster, and we've got our data spread out alphabetically, A through Z, across that back end. And the leader node is going to send a query down to one node and say, get me your rows. Another node, get me your rows. Another node, get me your rows. All those queries run parallel on the compute nodes. They take their result sets, they send them back to the leader node. The leader node aggregates them and hands them down to the client. This is how Redshift delivers that massive performance. Again, there's a interconnect between the leader node and those back-end compute nodes. This is a 10 gig Ethernet network. It's a private network just for that Redshift cluster. There's no other traffic running on this 10 gig network. So you've got super low latency connections between the leader node and between the compute nodes themselves. So if we need to move rows back and forth between the compute nodes and the leader, we can do it very, very quickly over that network. And then the connection to S3 for a couple of purposes. One, we talked about Redshift Spectrum and expanding your cluster to petabytes and exabyte scale. but also for real-time streaming backups. So Redshift is monitoring your traffic patterns, and in the background, it's snapshotting your data out to S3 automatically for you. All right, and here you can see the Redshift Spectrum fleet. So again, if you're comfortable and all of your data fits on your Redshift cluster, maybe you've got a 10-node cluster, maybe you've got a 100-node cluster, and your data's there, your queries are performing well, awesome. If you have a situation where you need, we talked about keeping 2017 and 2018 and 2019 in the cluster, and then going out to S3 for historical data. You can literally keep exabytes of data in S3 for 2.3 cents a gigabyte, even lower for some of the other infrequent access or single AZ storage classes. So you can now afford to keep all of that historical data around and query it through Redshift when you need it, and only pay for that when you access it. So super powerful feature with Redshift Spectrum's ability to bring in all that S3 data.
How does it know what's in the fleet versus S3? Do you have to tell it, or it automatically knows that?
You are one slide ahead of me. So the question was, how does Redshift know what's in the cluster and what's on S3? And I'm about to get to that. So again, you can think of Spectrum as an Amazon Redshift feature that allows you to query data in S3 without loading it into the cluster, potentially exabytes of data from your data lake. And again, we've got a fleet of Spectrum nodes behind the scenes that you guys don't need to manage. You throw a query at it, and we will bring up enough Spectrum nodes to manage that S3 data in a very performant way. And again, it's pay per query. You're only paying $5 per terabyte of scanned data. And again, we talked about using that very efficient Parquet file format in S3 to limit the amount of data scanned for very inexpensive queries. So here's the answer to the question. So you're all used to writing DDL in SQL, right? You write a create table statement, you give it your column list, you run the query. The difference here is that we're going to use this external keyword, right? We're going to go into Redshift and we're going to say create external schema, give it a schema name, and then we're going to go in and say create external table, give it a table name. That's the signal to store this metadata in that glue catalog that we talked about, that Hive compatible metastore that's going to map our DDL back to the underlying S3 resources. And that's the clue that we don't want to bring that data into the Redshift cluster. We just want to have this external table definition that's really just a mapping layer between the SQL DDL and the underlying S3 bucket and prefix structure and the underlying file structure in those S3 buckets. So once we've defined the external schema and the external table, we can then query it, and we can use both Redshift data and Spectrum data in the same SQL statement just by including that schema name ahead of the table name. So you could think of it as select columns from internal Redshift table name and external table name. You could think of doing a union across 2019 data in the cluster and 2018 data in S3. You could think of joining tables where I keep certain tables in Redshift and I do a join against tables stored in Spectrum. So you've got a lot of power and a lot of flexibility there just by using these external keywords. There's a couple of different instance types. You could think of these. These are just EC2 instances under the hood, right? But they are optimized for Redshift. There's a DC2 family and a DS2 family. The DC2s are more compute optimized. They've got NVMe SSDs. So smaller, high-performance disks, and then you've got DS2s, which are magnetic spinning disks, but much larger capacities. We go from 160 gigs on the DC2 large up to 2 terabytes on the DS2 extra large. So depending on whether your workload is compute intensive or storage intensive, you can pick the DC2 versus the DS2. I get a lot of customers who ask me how to decide. And again, the answer I give a lot of the time is build a POC and try it out. So if you were to spin up a 2-node cluster on DC2 larges, it would cost you 50 cents an hour. Throw some queries at it, see what the performance is. Maybe you decide you want 4 nodes or 8 nodes. Or maybe you decide, you know, my application is a little bit more data intensive than compute intensive. I'm going to spin up a 2-node DS2 extra large cluster and benchmark against that. And so again, the key is with this flexibility to very quickly spin up a cluster, throw some queries at it, get some benchmarks, experiment, fail fast, and build the cluster that meets your workload's requirements. So with that, I'm going to turn it over to Sudhir, and he's going to get into some interesting details and use cases.
Here, Ben.
Thanks, Steve.
So here, I'm going to talk about the cluster design considerations. So whenever you are designing a Redshift cluster, you always have to think about the 5 attributes. You can remember those attributes with the acronym SET-DW. S for sorting, E for encoding, T for table maintenance, D is a data distribution, and W is a workload management, which is also known as a WLM. These are the 5 real attributes you always have to think whenever you are designing. And if you are able to take care of these 5 things appropriately and optimized way, you are good to go with the Amazon Redshift. As the Ben said, Amazon Redshift uses the columnar storage in the behind the scene. So why we are doing the columnar storage? Let's see the difference between row versus the columnar store, so you will know what is the reason behind the columnar storage. So in case of row store, all the attributes of the rows are stored together in a block and in the form of physical file in the backend. But when you have the columnar storage, what happens? Each value, all the values of a particular columns are stored in one particular block. So it means each columns are going to be stored in different block. And when you run the analytic workload, what happens normally? You don't scan all the columns. You normally run the queries on 1 or 2 columns. So with the columnar storage, what we do, we just scan the relevant columns, the blocks which are relevant to those columns. You are just skipping all other data. So here in example, if you just want to scan all the social security number of all the residents, with the columnar storage, you have to scan the entire table. But when it comes to the columnar storage, you just scan, the blocks related to that particular column. So it reduces the I/O. So basically, it improves the performance of your delivery, and that's the reason why the Redshift is designed to choose the columnar storage, because it is optimized for the analytic workload. Now let's talk about the first attribute, which is encoding. Encoding is also known as a compression to a table. So there are dozens of encoding algorithms are available, like the bytes or run length mostly, and then LZO, Z standard. There are plenty. The Redshift documentation talks about all these in details. So here mainly I'm trying to focus, this is really important. And why it is important? Because it reduces the storage requirement, and at the same time it gives the best performance. Customer can get up to the 5x improvement in the performance. Even there is some overhead associated when you do the encoding, right? Because you are doing some compression and uncompression when you are scanning it. But still, the overhead versus the gain, the gain is very too much with the compression. So I highly encourage you to set up the proper encoding for all your tables. You might not see the major gain with the small table, but for the larger table, you will definitely notice the improvement in the performance. When the table is empty and you run the first copy command, you will see Redshift decides the right encoding automatically and intelligently. But if you have the data already loaded and you really want to validate whether the right encoding is assigned or not, what you can do it, you just run the analyze compression followed by table name, and then it will give the recommendations, and just take those recommendations and you can recreate the table to get the best encoding. There is a view which is called the PZ table def, from where you can verify what is the encoding options is assigned to each column of your table. Next attribute is the data distribution. So why we define the data distribution? Because it determines how the data is going to be spread across all the nodes of your cluster. And just remember, this is a shared nothing architecture, and this is the reason why the data distribution matters a lot. Because whatever is stored in slice 1, it's not necessary, it is not stored in other slices unless you have chosen the all distribution. So with certain distribution type like the key and even, it's really important how you have spread the data across all the slices. So there are 4 options, and when to choose with all this distribution, it depends on some factors. Like if you have a table, very small table, and you are not doing frequent modifications into that particular table, I would suggest go with the all distribution. And normally, the dimension tables are the good candidate for the all distribution. When you have a significantly large table and you know this is oftenly joined on particular column with some other dimension tables, then you can think of using the key distribution. When you are really not sure whether key or all, then last choice is the event distribution. But best fit for the event distribution is normally the standalone table, which you are not normally joining it. And but in some cases, but if you really do not able to determine what is the key and all, the table is significantly large, in that case also you can choose the event. The last option, which is auto, this is a recently introduced feature. What happens in this case, when you define a distribution style as a auto and you create a table, it starts with all distribution in the beginning, and as table grows, automatically it will be converted to the event distribution. Now let's see the example, right? Different distribution styles. So when here in this example, this is a deep dive table with 3 columns: audience, ID, location, and date. Now let's see how the data is going to be stored into the node, all slices with the different distribution style. So first is an even. So when you have even, the data is going to be stored in the round robin fashion. It's all, it's no logic, just round robin. The first record, when you insert the first rows, it is going to be just considered in the slice 0 of the node 1. When you insert the second record, it goes to the next slice, third and fourth, like this way. So with the event distribution, definitely you engage all the nodes to store the data and all the slices. But sometimes it is not very optimum, because the goal for defining the data distribution is to optimize your join performance. Because as it is a shared nothing architecture, and if you don't define the right data distribution and the data is spread across different slices, it might be possible that the dynamic distribution will happen when you scan the query, because still you have to join the data with some other slices, which is stored in different slice. Okay, slice you can think as a virtual processor. So you have the one compute node, and each compute node is further partitioned into the slices. So slice means you get some small portion of the memory and compute from that particular node. But slices is independent, they can run all in parallel, and they store, each slice store the different information.
Is it like a core?
Virtual processor. Not exactly the physical core, but they are the virtual core. You can think like that way. Yes.
So how do you decide how many slices should
Yeah. The question is how to determine how many slices. So as the Ben said, there are 2 choices, right? Either you can go with the DS category or DC2 category, and the number of slices are pre-configured. Like if you choose a DC2 large, you are going to get the 2 slices in each node. When you are creating a cluster DC to 8XR, you get the 16 slices in each node. So it is a predefined. The only thing you get option which type of EC2 instance you want behind the scene, and you will get the number of slices based on that. Next is a key distribution. So in the given example, suppose you, with the key distribution, first you have to determine which key you are going to use for the data distribution. And consider you have chosen the location column as a data distribution. And the same record, right? The previous example, if you insert the first record and consider the SFO entry, the hash key of the SFO comes into slice 0 of the node 1. It is stored here. The next entry is JFK. It may fall into the different slices. When you enter the third record, it's again SFO. So hash key is again going to come into the same slices where it was stored earlier. Same for the JFK. So what you noticed here, if you are not defining the right data distribution key, you will see the skewness in the data. And in this example, just consider you have loaded only 4 rows, and all 4 rows are stored only in the node 1. Node 2 doesn't have any data. And when you query it, only you are going to engage the node 1 because node 2 doesn't have any data. So this is not good key candidate to store your table. Yes?
So what's a use case for even distribution?
Even distribution, see, you should always think about first try to define as a key distribution, not even, because even it is going to distribute evenly, but during the scan time, you will see the dynamic redistribution of the data from one slice to a different node or one slice to a different slice. So to avoid the network traffic during the scan, better to choose the right distribution key. But suppose if you have the standalone table, you know, right, one large fact table, you are not joining with anything, then it's good to choose an even distribution as a first place. If you know that your table is not going to join with anything, then better to spread it across all the slices so that whenever you scan, you give the equal amount of work to all the nodes of your cluster. The same example, if you choose the audience ID as a distribution column, so because you have the different audience ID for all the records, you can see the data is stored in the different slices. So even with the, so what is the takeaway from here? If you define the right distribution key, you can see the even distribution across all the slices, and you will see the good performance when you do the joining with other tables. Yeah. Composite keys? No, so in data distribution, you can define only one column. You don't get options to define the multiple column as a data distribution. So the question is, can the column be a composite? So if you are storing the data, you know, the join of 2 columns, yes, then you can define it. Ultimately, it will be treated as a 1 column. But the way what you are trying to store it, the 2 values from 2 different columns, yes, you can do that way. Exactly. Mm-hmm. Yes, exactly. Thanks for pointing it. And now the all distribution. With the all distribution, the entire table is going to be stored in the slice 0 of all the nodes. So the same record, see, the first record, it's stored in both the nodes. Second record, third record, fourth record, but only the first slice. So this is very good in case of when you don't have the appropriate column, which is going to be used very often with the joins, and the table is not very large. Because if the table is significantly large, just consider terabytes, then you are storing the 2 copies, right, in the cluster. So you are, at the same time, you are consuming more space into the cluster. But the benefit is other side, even the same data is not co-located in the same slices, you are not doing the dynamic distribution during the scan. The data is physically available into the node. So if the data is co-located into the same node, it is definitely going to deliver the fast result. Now let's talk about the zone maps. So zone maps are the in-memory metadata information for each block. It contains the minimum and the maximum value which is stored into that particular block. So why it is important? Because just after scanning the metadata, this zone map information, the Redshift query optimizer will know, okay, my data range falls for this block or not. If it doesn't fall, it is not going to scan. So it reduces the number of IOs you are going to perform to scan the table. Now let's see the third attribute, which is the sort keys. Sort keys define the physical order of your data into the disk, how the data is actually going to be stored into the disk. And you get two options. There are two types of sort keys you can define. One is a compound sort keys, and the second is interleaved sort keys. In the sort keys cases, you can define the multiple columns. It's not necessary to have only one column in one sort keys. And if you can think the sort keys as an index, but it's not actually an index. But the way it functions, you can think, yeah, this is a kind of index for a table. And when you have the sort keys defined, and because zone maps information is already stored, you can see with the help of the sort keys, you reduce the number of IO calls. Take the example of this. So you have the deep dive table, same table. When the table is not sorted, you can see the same record, maybe just 9th of June 2017. It might be spread across, just multiple blocks. Here, 3 blocks. But if the data is sorted, all data can fit in the same block or maybe the subsequent number of the blocks. You can see the number of IOs immediately reduced. With the same data sets, just after having the right sort keys. So you eliminate a lot of IOs. So let's start with the compound sort keys. This is a default option. If you don't put anything like any specific keyword like the compound or interleaved, by default it is a compound sort keys. In the sort keys, as I said, you can choose the multiple columns, but the column order matters. Because if you are coming from some different RDBMS background, people might think, okay, you have created an index on 3 columns, and let's take the example of Oracle, right? And you are not using the first column, still you take the advantages of the the indexes using the skip scan operations. But if you have defined a sort keys on, just consider column A, B, C, and you are not running. And when you are running the query, and in the where clause, if you are not using the column A, you are not taking the advantage of the sort keys. So in order to take the advantage, all those columns should be coming as as a predicates in the where clause. If it is not, then you are not taking the advantage. So always think which columns you are oftenly used in the where clause, and try to create sort keys in those columns. And another thing, the column order matters. So suppose you know that column A, B, and all 3 C, all 3 you are going to use it very oftenly. So in that case, I will say put the column which has a low cardinality as a first column. Because ultimately, the way you traverse to scan the block, if you have pruned most of the number of blocks in the first scan itself, you are not scanning more number of blocks, because that is the next step. That's the reason I said this is a kind of index. It's not really the physical structure, it is another metadata stored in the block itself. So the second option is interleaved sort keys. There are some use cases, right? It is possible that you have created a sort keys in 3 columns, A, B, and C. And sometimes you are accessing, you are doing the query and put the where clause on just a column A, sometimes column B, and some column C, and might be some combination. But still you want to take the advantage of sort keys. In that case, this is a one. Interleaved sort keys can help you. If you define, when you are creating a sort key, you are defining the sort keys, and you mention it as like the interleaved sort keys, then Redshift gives the equal weight to all columns, whatever you have chosen in the as a form of sort keys. So irrespective whether those one particular column is used or not, still you are going to take the advantage of sort keys. I know this looks okay. This is a one solution, right? By default, why not to jump on the interleaved sort keys? I will suggest don't start your table design with the interleaved sort keys. This is a last option. Based on what we have seen from the customer, 99% of the use cases are just fit for the compound sort keys. And the second thing, interleaved sort keys, there is some overhead associated. Because of the complex structure, it is based on Z index, it is really complex. And in order to maintain the Z index, when you do some DML, it adds some overhead. And when you run the vacuum, because that is another process, I think, in the later of the sections, Ben is going to talk about that. So in order to just to delete the, clean the deleted blocks, that is a vacuum is a process. Vacuum runs longer. So whenever you are thinking about having the interleaved sort keys, I will suggest open a case with Amazon Redshift, support case, and then take their guidance as well and use it very cautiously, because I know one place it gives an advantage, but other place there is some disadvantage also associated. But it doesn't mean that you cannot use this. Some people are really using it and taking the advantages. Now let's talk about the 4 component, which is a WLM. Amazon Redshift provide a sophisticated tool to handle your workload, which is also known as a WLM. So through the WLM, primarily you control the concurrencies and the memory allocation. Whenever you create a Redshift cluster, default parameter group WLM queue, parameter group will come, which will have one super user queue and one the user queue with 5 slots. When I say the 5 slot, it means only 5 queries can run concurrently at the same time onto the cluster. Which is normally, sometimes you might think because if you have not created your own WLM queue, and the default is coming with 5 connections, and if you are running more queries, even though cluster can have potential, you might say, oh, the cluster is running very less query at a time. It is possible. And major disadvantage with having just default user queue is, because if you will have some mixed workload, right? Some long queries are running, some short queries are running. And if too many long queries are entered into the cluster, the short running queries will be just waiting. And ultimately, it will give the unpredictable performance, right? The user might think, hey, my query was running in 2 seconds, why it's just, because it is waiting, but from end user perspective, it has not written the results. So you might see the unpredictable performance. So how can you avoid that? Simply create a multiple WLM queues. Simple example, you can have the 2 WLM queue, one for short user and one for the long running users. And there is ways you can divert your queries to specific designated queue. So like you can use the user group or you can use the query group to define, okay, these queries are the candidate for short queries and these are the queries candidate for the long group. Yeah. Thanks. The question is there any cost associated with the WLM? The answer is no. It comes with Redshift. You don't have to pay. You can create even 3 queues, 4 queues. In reality, people normally create 2 to 3 WLM queue. One for ETL purpose, where they are really doing the heavy intensive jobs, and there they allocate more memory with less number of concurrent sessions. Then another queue people thinks for the dashboard, where you allocate the less number of memory, but you can handle the more concurrencies. And third one for the ad hoc purpose. So yes. So I think, I don't have the slide here, right? You can see, you can define the memory and the number of slots. You can really define it by own. And each WLM queue can have the different memory percentage with different number of concurrent slots. Over the period of the time, the Redshift engineering team has added many features with the WLM, based on the feedback we are constantly hearing from the customers. So one is a SQA. the first great feature. The SQA is a short query acceleration. What happens? Amazon Redshift uses some machine learning machine algorithm to determine, okay, these are very short queues which can be finished less than 10 seconds and 20 seconds. Why to put in some different WLM queue and keep waiting it until it really ends? So what it will do, it will run the algorithm. It's constantly running. It's not like that it will run on that time. So we run the machine learning all the times behind for your cluster. And as we detect, hey, this is the short queries, and you have enabled the SQA option for your cluster, it will take your jobs and run into the dedicated space and return the results. So it will not take the route of the standard WLM queue you have defined. This is really great. And you can, with the SQA, you get option. You can define, okay, 0 second to 20 seconds, or you can just leave it on everything to the Redshift itself. So if Redshift thinks, okay, this is my 3 second, 4 second query, let's run it through the SQA or not. Second is concurrency scaling. This is a recently introduced, I think last week only we announced, now it is in GA. It's a really cool feature. And after the concurrency scaling, now you can scale your, scale the compute and storage separately. So what does it mean that? Suppose your cluster, you have created a cluster, maybe 10 node cluster or 5 node cluster, and you are able to run certain number of the jobs. But at some given point of time, high traffic may come. And then your queue will be piled up. How you are going to handle it? If you have enabled the concurrency scaling, then Redshift will spawn a new cluster, transient Redshift cluster behind the scene, and it will route the queries to your transient cluster, deliver the results, and as the query goes down, the transient cluster will be deleted automatically. You don't have to do anything. It will happen automatically behind the scene. So with the concurrency scaling, you can achieve the consistent throughput from your cluster, even when the load is high on your cluster. And definitely there is some cost associated, right? People will think, hey, because you are creating another cluster. The good thing is, most of the customers are able to use the concurrency scaling without paying anything. Because we give 1 hour credit every day if you have the Redshift cluster. So every day you get 1 hour free. But if you are crossing the 1 hour, more than 1 hour, then you will have to pay the on-demand price for that. The last thing is the dynamic WLM. So this is another common feedback we hear from customer. We say, right, create multiple queues and determine, okay, what is the number of slots you want to configure it. And sometimes, due to many reasons, right, people are not able to guess it. What is the right number of slots for my WLM queue? And what happens? Because suppose you have the WLM queue and you define 50% memory and you are running 2 sessions. It means that you are giving 25% of the memory to each session, even though you are able to use it or not use it. Maybe you are just running very small query. With the dynamic WLM, the good thing is Amazon Redshift run our own algorithms to determine what is the best slot count for your WLM. So it will, based on your traffic, based on your workload, it will decide how many concurrent queries to run in your cluster. So in this way, no need to set up how many slots for your WLM. It will be handled by Redshift itself. Really great features. This is in beta, not in GA, but you can still enroll and you can request for access if you want to do some POCs. WLM best practices. In Redshift, WLM number of concurrent slots are limited to the 50, but I will suggest don't configure your parameter group for more than 15 connections. Because Redshift is designed to give the best throughput. It's not the OLTP transaction systems, right, where you want the immediate response. The customer will have requirement like this. I want to run 1,000 queries in per second or maybe 10 minutes. So it doesn't matter, each query is, 1,000 queries running immediately. You have some window, okay, 1 hour or 10 minutes to run these many jobs. If you define the less number of sessions, it means you are giving the more resources to your job. So your jobs can finish very fast. And it is really optimized to deliver the best throughput. I will say don't go beyond 15. Maybe if you have just dashboard kind of queries, you can think of 20 connections, but I mean 20 WLM slots, but normally less than 15 are good. Second thing is, yes, you can create up to 8 custom WLM queue, but I will recommend you to limit to 3. And anyway, you have some additional feature like the concurrency scaling, SQA. Anyway, you are handling some of the traffic there or too. So limit your number of custom queues to 3. Second thing, third thing, for different type of workload, use a different WLM queue so that the same patterns users can get the same performance. Like I explained, right? Sort users to run in sort query group, and the long running user divert into the long running queue. The fourth thing is keep the 5% memory unallocated. So as I said, right, you can define the memory for each WLM queue. So let's say you have a 3 WLM queue. Option is define, just I'm giving a random option, 30, 40, 30. And you are giving the 100%. But there will be some situation, maybe you define 30%, but you might need some little bit more memory. And if you reserved some memory unallocated, like 30, 30, 35, you reserved 5%. Okay, that 5% can be allocated to anywhere based on the need. So it is recommended to leave the 5% memory unallocated. And then definitely enable the SQA and the QMR rules, because it really helps. I think I have not talked about the QMR rules. The QMR rules are, I can say, they are the performance-based some matrices, and you can enforce some rules. Like if you can create some rule, if your query scans more than 10,000 blocks, okay, hop to the next queue, or abort the query, or just log the query, and you can do the further troubleshooting. You can play, I mean, most of the parameters of the WLMs can be changed dynamically. I mean, you can play around it, like the number of connections, memory, percentage allocation. So like night time, you might think, okay, I'm running heavy ETL jobs. ETL WLM queue, maybe give the 60% of the memory. In the daytime, your reporting is happening mainly. So in the WLM queue responsible for reporting, give them more memory. You can do this flexibly, but someone has to do it, right? So either build your own algorithms or own logic, put it in Python or EC2 and run it, or you can take the advantage of some GitHub codes available provided by the AWS. Just deploy it, and you get some configuration options. And even you can kick off through the Lambda also. At this time, okay, make this WLM like this, and the different time you can change the WLM parameters. Now, I want to hand off to Ben.
Right, thanks a lot, Sudhir. Okay, so just a couple of more modules here on Redshift. So at this point, we understand a lot about the internals and the performance tuning of Redshift. Let's do a deep dive on getting data into Redshift. So there's a number of options for loading data into Redshift. There's definitely some best practices here that we want to encourage folks to adhere to. So it is possible to do row-level inserts into Redshift, but this is not the most high-performant way to do it. Basically, we have taken the copy command and we've optimized the Redshift copy command to work with Amazon S3. And there's actually a very small bug in this slide. Unfortunately, it was given to me as a bitmap, and I couldn't didn't have time to recreate the entire image. But basically what we're saying here is that using the Redshift copy command, we can break our input files into smaller files, right? So if, let's say we've got a 1 gigabyte file, we might cut that up into 10, 100 megabyte files, or if we've got a large data set, we might use glue, or we might use the Linux split command, and we want to crack that file into smaller pieces and load them in parallel. And so the Redshift copy command is going to allow us to do that. There's also some operators like unload and create table as that are going to be much more high performant than just doing row-level inserts. So we definitely encourage folks to take a look at the copy command when they think about loading data. So what does that look like specifically? So again, you go to your SQL command line. You're going to say copy table from location. The location is going to be an S3 bucket or folder. You're going to pass in some credentials. There's actually two methods on the slide. I definitely don't encourage method number one. So it is possible to pass in your secret key pair to the copy command. This is absolutely not a best practice. Why? Because you're going to take this load script and you're going to check it into GitHub, and that's going to get you somewhere you don't want to go. So the best practices are to use this IAM role and specify an ARN, and that role will have permissions to do a load into your Redshift cluster. So definitely take the time to learn about setting that IAM role up and specifying that ARN in the copy command. And then you're going to specify the region that you're targeting for the load. There's a bunch of options for the copy command. We talked about Parquet files a lot. So in December, we announced Parquet support for the copy command. So in addition to CSV, JSON, Avro files, we also now support Parquet files. There's a number of compression and encryption options. Again, we want you to really have high performance copies so that you can do these frequently to keep your data loaded as frequently as possible, right? So we don't want the case where we're loading data once a month. We'd love to see you guys be able to do it every week, every day, every hour, every 15 minutes. We want this to be as close to a real-time operation as we can to make that data available to your user. And so the more performance tuning you use on the copy command, the fresher your data is going to be in that data warehouse. And again, there's some mild transformation options, like you can drop columns and stuff. This is not meant to be an ETL tool. This is just really to get that ETL cleaned up data into Redshift as quickly as possible. But you heard Sudhir talk about nodes and slices, and the Redshift copy command. Let's say we've got a cluster and it's got a 10-node cluster. We want to have at least 10 input files so that we can load them all in parallel, right? So if we've got one big input file, we're going to hit one node in the cluster, and we're going to dump that entire file into that one node, and the other 9 nodes in our cluster are going to sit idle, right? So what we want to try to do is, again, either using the Linux split command or ideally AWS glue to ETL it into smaller files that we can then move in parallel for maximum efficiency. So basically have as many input files as you have slices. So in a DC2 large, we've got 2 slices. In a 10-node cluster, that's 20 slices. You want to have 20 input files or 40 input files, or some multiple of 20, so that your load can happen as quickly as possible. And then again, unloading. So there's cases where you want to unload the entire database and store it in S3. Maybe you want to recreate a test environment. So you're going to dump out production. You're going to fuzz that data to get rid of any PII. And then you're going to put that data into a test environment. You'd use the unload command for that. And again, supports a number of file formats and a number of different options. And integrates really well with S3. So we talk to customers all the time. They love the performance of Redshift. It's the right tool for their large-scale data warehouse workloads, but they said it was a little bit of a pain in the neck in terms of the care and feeding of the cluster. And they asked us, what can we do to make operating the Redshift cluster a little bit easier? And so we recently introduced the ability to do an auto-analyze and an auto-vacuum on the cluster. And basically what that means is instead of you having to have a specific step in your workflow where you vacuum to reclaim the space occupied by those dead rows, we're going to do that in the background. And instead of you having to have a specific maintenance task to update your indexes and your metadata, we're going to run auto-analyze in the background, and we're going to keep all that metadata updated for you. So again, these are steps that people traditionally had to build in. We've copied some data into the cluster, and now I have to run analyze to update all my indexes. Now we're going to do that behind the scenes for you. Yeah, so there is some intelligence. So the question was, when does it run? So there is some intelligence built into auto-analyze and auto-vacuum about when it runs. And as Sudhir said, there's a lot of self-awareness in the Redshift cluster in terms of its performance and self-healing and optimization. And so this will look for dips in your workload to kick in because there is a performance penalty. These are necessary operations, and I have customers that are afraid to run analyze and afraid to run vacuum because it's going to slow down their cluster, and this leads to disaster because your indexes become out of date and your queries start to slow down and your cluster starts to fill up because you've got all those dead rows in there. So you absolutely want to do maintenance on your cluster. It's not something that can be kicked down the road. You can't kick this can down the road. And to make that a little bit easier for customers, we've implemented these two functions, auto-analyze and auto-vacuum, that will make some intelligent decisions about when to run and run often to keep those metadata catalogs and that space utilization optimized. And then resizing. So there's a new option called Elastic Resize, and this is going to give you the ability to add nodes of the same type to your cluster. So let's say we've got a 4-node DC2 large cluster with, I don't know, what is that, 640 gigs of storage, and we want to add another 4 nodes to it. Traditionally, we would put the cluster in read-only mode, and we would copy the data to a new cluster, and this would take hours. This is a lengthy process. With Elastic Resize, we're able to add nodes of the same time very, very quickly in a period of minutes. Now, the caveat there is if you want to switch from let's say DC to dense compute nodes to DS to dense storage nodes, you're going to have to use the traditional classic resizing method. But again, this really makes it easy to provision your cluster for exactly the number of nodes you need for your workload and then grow it as required. So we encourage folks to create a cluster with a certain amount of headroom, and then when their data starts to fill up and maybe they hit 70%, they can allocate 4 more nodes, and then they get to 70% and they can allocate 4 more, or whatever the number is that makes sense for your environment. And that way you're not over provisioning with a bunch of idle capacity. Yeah, question?
You may have covered this earlier when you first talked. Was there any region compatibility?
Yeah, so Redshift cluster is going to run in a specific region. I would have to check the AWS regions page to tell you every region it's available in. But, yeah, exactly. Yep. Cool. And then there are a lot of resources online. So if you go to aws.amazon.com/redshift, you can get information on data warehousing. There's an ebook up there. We've got blog posts, customer success stories. Again, this is how we learn. We go visit with customers. We understand what they're doing, and we take those best practices. Build a proof of concept, fail fast, right? Spin up a 2-node DC2 cluster for 50 cents an hour. It's 320 gigs of storage. Throw some queries at it, write some benchmarks, and get a sense of like, hey, you know what? This is perfect for my workload. Or, you know what? I really need dense storage instead of dense compute. Tear down the cluster, only pay for what you use. And it really gives you the freedom to experiment. You know, I talked about the old days of like getting purchase orders signed and then ordering hardware and waiting for it to arrive and then getting it racked and getting the software installed. You had to guess right. It was very difficult to go back to the CFO and say, I didn't really want dense compute. I wanted dense storage, and I need another SAN, and that would not, get you where you wanted to go. Whereas with Redshift, we can provision customers and clusters in minutes, do a POC on them and tear them down. We can grow them and shrink them elastically as our workload dictates. It gives us a lot of freedom to experiment and to build out new workloads and new POCs. So that's everything I have today. Thank you so much for listening, and thanks to everybody on Twitch. I'll see you next time.